All right, guys. Want to start. Basically, I've got three of these things that I want to talk about today. Each one shows a little bit different kind of structure to the graph, okay? But they all have kind of similar characteristics that we're going to use to come up with that graph. Now, it takes time to do these, all right? But our alternative is just to start choosing X values and evaluating, which is even more time consuming, kind of creating a T-chart type thing and plotting points that way, which is time consuming, and it's really not all that comprehensive, it's not a lot of safe because you don't know which X values to choose, okay? Kind of like think about back when I first graphed X squared, you first graphed X squared. If you just graph the positive values, if you go 0 and then go integer or positive integers, you're not going to get a comprehensive graph of X squared, right? You're not going to get that full parabola. So that's the same idea here. We're not sure what X values to really start using here if we want to do a T-chart. Okay, now, we might come down to a T-chart here in a little bit. This is the idea. I'm going to write this stuff up here on the board for pretty much every time that we do one of these. I'm going to try to figure out what my vertical asymptotes and my holes are, okay? And those two things kind of go together, okay? Or I don't want to say kind of go together, they do go together, okay? And really, you want to look for holes first, and I'll talk about that in a next couple examples. This one doesn't have holes, but we're still going to kind of write that the concept down. The next thing I want to do is find horizontal asymptote, okay? Or it might end up being what we call an oblique asymptote or a slant asymptote, okay? Slant meant it was linear, okay? And we'll see maybe tomorrow 1 or 2 examples of that. Oblique means it could be linear, it could be quadratic, cubic, quartic, or whatever. And then graphing those. So every time that when we do a horizontal asymptote, we have to graph that horizontal line, right? Okay. Well, when I do a slant asymptote, it's going to be a linear. It's going to be like graphing a line from algebra 1. Okay. It's going to be in y equals mx plus b form. Okay. I have to graph that. I have to know how to do that. Okay. Well, if it's quadratic, it's oblique, I have to know how to graph that. If it's cubic, I have to know how to graph that. If it's quartic, I have to know how to graph that, right? So as we start getting to cubic, quartic, quintic, that type of thing, we're now within this problem of rational functions. We're going back to the beginning of chapter 3 and having to do that stuff in section 3.1, 3.2, 3.3, all for just the asymptote of this problem. Does that make sense? Okay. So you kind of get, when they get more complex, these asymptotes, you kind of get problems inside problems, or procedures inside procedures. Look for those. We're going to then, every time we look for one of those or find one of those, we're going to see if we cross it. Okay. Obviously, those things go together. The next thing, pretty straightforward. We'll look for x-intercepts. We'll look for y-intercepts. Okay. You only have one y-intercept, right? It's got to be a function. It's got to pass the vertical line test. And then, if necessary, we'll do a T-chart. Okay. And I do think a lot of times it is necessary, but it might not necessarily be organized as a T-chart. You might only need 1 point. Okay? You might just choose off an X value, evaluate, and see what you get. Okay? To where you don't organize your work in kind of a 2-column T-chart idea. Does that make sense? Okay. But we might need that. A word that you might see for holes is point discontinuity. Okay. Remember what continuous meant, right? Continuous meant that I could trace the graph with my finger without lifting it, right? Okay. Now we're not going to be able to do that with any rational function because of the asymptotes. Okay. So you got to lift your finger over the asymptotes. However, each little region within kind of that is kind of segmented by our asymptote, each one of those regions a lot of times is continuous. Okay. Within certain intervals. But if I've got a hole, it won't be, and I'll have to lift my finger to jump over that one point to continue graphing. That's what we call point discontinuity. Okay. So those are the things that we're going to be interested in. Okay. Now, vertical asymptotes in holes. Okay. A hole, and we'll get into more of this later. But a hole is found at common factors, or found when you have common factors. Okay. So if I look at my numerator, 2x minus 1, I have none of those in the bottom. If I look at x plus 4, I have none of those in the denominator either, right? So there's no common factors. So in this case, I have no hole. Okay, so it's not applicable here. If there were common factors, the 0 of that common factor is going to be where my hole is. Okay, so we'll talk about that later. No holes here. Then the reason I do that first is because if you have a hole, let's say that I had like an x plus 4 up here and an x plus 4 down here. Initially, the x plus 4, I'm thinking, what's division by 0? I'm going to have an asymptote there. Okay? Well, when they cancel, it's not an asymptote anymore, it's a hole. Does that make sense? So a hole overrides asymptotes. So it makes sense to do those first. Okay? I don't have any here, so now I can look at the denominator. For vertical asymptotes, okay, is where your denominator, you might see it written this way, you might say zeros of denominator. Okay. Well, the zeros on my denominator will be located at x equals 1. It's x equals negative 2, isn't it? Okay. So this is the expanded version. This is the factors. Kind of skipped over. I wanted to give you in the factor form so we save a little bit of time. Okay. Like you said. But we should be able to recognize that when we do factor that bottom, division, when x is 1, we get division by 0. When x is negative 2, we get division by 0. So those are going to be, when we graph this, our vertical asymptote, which is the visual cue that tells you you cannot have an ordered pair on that vertical line. Okay. The next thing we want to do is find our horizontal asymptote. Okay. Now, give me 1 second. All right, so our horizontal asymptotes, remember what our horizontal asymptotes are? They are strictly just the, right here, it's open. The horizontal asymptotes are just strictly talking about end behavior, okay? So if we think about what happens in regards to end behavior, the only thing that impacted end behavior for polynomials themselves was that leading term, right? Okay? So now because we have a leading term divided by a leading term, that is what dictates end behavior here, okay, for rational functions. So when we look at 2x squared over x squared, okay, those are our leading terms. If I do that division, and this is usually the way I do it, I'm not saying it's the right way or the only way, I write it this way. I write that way. I do the cancellation, leaves you with just 2, right? Where I'm left with just a numerical value, that's my horizontal asymptote. If I'm left with a variable component, as we'll see in the next example, I then substitute very large numbers of x and see what happens, see what I get, okay? Do I get something like infinity or do I get something like 0? And that will then tell me kind of my next step or what my asymptote really is. So here we get a horizontal asymptote at the line y equals 2. Does that make sense? Okay. Now, sometimes you won't be provided this. Sometimes they will not give you the expanded form. Okay. Do I need to expand this thing completely to find those leading terms? No. Okay. My leading terms, if I just think about foiling or just the repetitive foiling process, you got more than 2 terms to FOIL. So you've got 3 binomials or 4 binomials or whatever. Isn't your leading term always first times first times first times first? However many firsts you have. As long that might be contradicting in some problems if your variable term is not coming first. Does that make sense? So I would not maybe say that if it was -1 plus 2x. Does that make sense? Rewrite it so it's 2x minus 1, and then you can go through and do all that. Okay? So first times first times first times first will give me my leading term. So in the top, it's 2x times x, right? Give me my 2x squared. On the bottom, it's x times x, give me my x squared. Okay? So even though if the problem is already factored for us, the expanded version is still useful. But do I need the entire expanded version ever? I don't think you do. Okay? So we benefit from them giving it to us in factored form, I think. Now we want to know, do we cross the horizontal axis? Okay? Well, if that's the equation for my asymptote, and I'm going to come up to this. Yeah, I'm going to use it. I guess the expanded version, it is nice in finding the horizontal asymptote. It's not as bad as factor. Let's use a factor just so. I think if I gave you the expanded version and you use that, you would know exactly what to do. Let's do the factor one. If I've got these two things, they both have y equals, right? If they cross, if these two graphs intersect, then for that y value, they both have to be the same, don't they? And they have to have the exact same x value. So what that means is we got really a system of equations here that we got to check. We're going to take 2x minus 1 over x, times x plus 4 over x minus 1, x plus 2, and we're going to set that equal to 2. Okay, this is a rational function. This is r of x, and this is your horizontal asymptote, right? We want to see if they're ever equal. Okay. Now we get that, and if you remember back to like the first chapter that we worked on solving equations like that, right? Okay. We multiply by the LCD here. Okay. So the LCD is going to be this x minus 1, x plus 2, so we get 2x minus 1, x plus 4 is now equal to x minus 1, x plus 2. Okay. Now, this is the reason I was looking at this in the factored form. If you ever are using the factored form like this, now what do I have to do? What do I have to do to be able to solve for x here? I have to pull all that out. I have to get rid of those binomials and get it into, some quadratic expressions or whatever on both sides. Now, the nice thing is that we do already have this here. So I'm going to kind of cheat a little bit. 2x minus 1 x plus 4 should give me 2x squared plus 7x minus 4, right? On the right-hand side, x minus 1 times x plus 2 should give me this. So I'm going to double that, and I should get 2x squared plus 2x minus 4. So I get that. Does that make sense? Now what happens to my 2x squared? Cancel out. Okay. I will now have, 5x equals 0, right? If 5x equals 0, what's x going to be? X is 0. So when I get a numerical response, and 0 is a number, right? Sometimes people see 0, oh, well, that means I don't have one. No, you have one. You cross the horizontal asymptote here at x equals 0. So cross horizontal asymptote at x equals 0. What will be the y value that I'm crossing the horizontal asymptote at? It would be 2. Okay? So 0, 2 is that location that you cross your horizontal asymptote. Okay? Questions on that? All right there? Okay. The next thing we're going to try to do is we're going to find our x-intercepts. Our x-intercepts are when what coordinate is 0? Y is 0. Okay? So this is when a factored form is useful. I'm going to say that the y value is 0. Then I have 2x minus 1, x plus 4. Now I have x minus 1, x plus 2. Okay? Now, I'm going to highlight that denominator. Does it ever matter when I'm trying to find x-intercept? Does it ever matter what that green stuff is? No, because the way I'm going to start to solve this, the way I try to get rid of this, it's a rational equation, and we try to get rid of fractions as soon as possible, right? To get rid of fractions as soon as possible, we multiply by the LCD. Well, the simplest LCD here is to say that that's 0 over 1, and then multiply by 1, x minus 1, x plus 2 to both sides, right? When I do that to both sides, doesn't this wipe away here? And when you multiply 0 by that stuff, it's still just 0, isn't it? Okay. Now, the idea is it does not matter what the denominator was. Never matters what it is. When you multiply it by both sides, if one of those sides is 0, it's always going to vanish. Okay? So a lot of times you'll see them right, that your x-intercepts can be found by taking the zeros of your numerator. Okay? So zeros of the denominator give me my vertical asymptotes. Zeros of my numerator give me my x-intercepts. So in this case, my x-intercepts are going to be, what, 1/2 and -4? Okay? So that should be pretty easy once we already have it factored. X equals 1/2, x equals -4. And those are my x-intercepts. That looks like I wrote it as my y-intercepts. I know order pairs, right? Okay. Now y-intercepts, again, looking at either one of these versions, okay, when I just had a polynomial, let's just say I'm looking at just that polynomial stuff. What is the y-intercept of that polynomial? Say again? -4. -4 would be the y-intercept of that numerator, right? Okay. What is the y-intercept of the denominator? -2. So what do you think the y-intercept of r of x is? It's 2. It's the quotient of -4 and -2. Does that make sense? Okay. So your y-intercept is a x value of 0 and a y value of 2. Okay. I think that's the easiest way to figure it out. Okay. We understand how that constant term impacts a polynomial itself. So the quotient of your constant terms in your numerator and denominator will give you your y-intercept. Now, obviously, if it's in factor form and I don't have the expanded version, okay, maybe it makes sense to do this. Well, if I'm looking for my y-intercept when x is 0, right? And you can do that over here as well. If x is 0, doesn't that go to 0? 0, 0, 0, and we're left with -4 over -2. So over here, same thing. That goes to 0, it goes to 0, 0, 0. So you're left with -1 times 4 over -1 times 2. So it gives you 2, right? Okay. Another way of doing it, okay, kind of how we talked about finding, kind of how we did the horizontal asymptotes instead. We did first times first times first, and then divided those things, right? Well, if I look at this thing here in factor form, isn't last times last times last always going to give me my constant term? Okay. So you can do it that way. You can take my last, my -1 times my 4, my -1 times my 2 on the bottom, and then do that quotient. Okay. Regardless, you get 0. Is that all right, everyone? Yes.
Well, so in this case, since we already knew that it was 0, 2, because that's where we crossed our horizontal axis.
Yes, that's another thing, and those are little things that we want to kind of maybe pick up on eventually. What Derek is saying is because we already knew we crossed our horizontal asymptote at 0, 2. Okay, so we obviously that has to 0, 2 is a y-intercept, isn't it? It's on the y-axis. So that's something that you can look at and realize, well, I've got that occurring, so then my y-intercept cannot be anything different than that. Okay. Another time that you see something like that is occasionally you'll get a vertical asymptote at x equals 0. Okay. Not a vertical asymptote at x equals 0. X equals 0 is just the y-axis, right? Not a vertical asymptote passing through the y-axis. Can I have a y-intercept? No. Okay. So then you don't even do that. Does that kind of make sense? So little things like that, and paying attention, not being a robot, paying attention to things that you've done, what their implications are, and how they might impact other aspects of your arithmetic, can kind of maybe save you time a little bit, okay? I always have somebody every year that does every single thing for every single problem without any thought, which is fine. It's very time consuming, and they usually run out of time on tests and quizzes because they're not using the mathematical part. They're just doing the calculator stuff. Does that make sense? Okay. Same. No, you can never have two line inputs because then it won't be a function. All right, so the next thing we do, and I just think it's best to use some graphing tool, guys. If you want to use GeoGebra or Desmos, doesn't matter. Do not use your TI-8384 with these. They're kind of a pain in the butt. You can't really graph it because of the Y equals already defined for you. It's kind of hard to graph like your vertical asymptotes, your horizontal asymptotes, all that kind of stuff. At least your vertical asymptote. So we have a vertical asymptote x equals 1 and 1 at -2. We had a horizontal at 2. What I like to do, just to make things convenient so I like to color them. Even if I'm doing it by hand, I like to have like a colored pencil or something because a lot of times you're going to get asymptotes that go over the top of your axes, and it's really hard to realize that that's there. Does that make sense? If I have color on top of it, it's a visual cue or reminder that I've got an asymptote there. Okay, so we've got those things. The next kind of thing we want to kind of put in here is we didn't have any holes. So we skip that. We're across our horizontal asymptote of 0, 2, so I'll put that in. 0.02 in. Okay. I'm going to find our x-intercept, so 1/2 and -4. So 1/2, comma 0, -4, comma 0. And then that's it, right? So that's all the information. The y-intercept was redundant. It's at point A again. So here's the nice thing. We currently have enough stuff to get about 2/3 of this graph completed. Okay, because of how we understand what our arithmetic, what our algebra is telling us, and kind of our understanding of what these asymptotes kind of structure our graph, our orthograph is. If you go left to right, I'm going to start over here with these things. I got C down here, right? Point C is a x-intercept. As I move to the left, I move that direction on my x values. Okay? My y values are going to start to show the end behavior. Does that make sense? Okay? So my y values are going to go up. Okay, now will I ever cross that blue line again? No. At point A, that is the only point that my algebra provided me a crossing of the horizontal asymptote. Okay? So I do not cross to the end. As I move to the right of C, and this is the idea, I don't cross it again. So as I move to the right of C, there's no way that my graph would come up like that. Does that make sense? Because if it did, I would have had the math that says, well, you crossed the horizontal asymptote again at like -2.5 or something like that. Okay? We don't cross it again, so we can't make a turn like that. So we're going to approach that asymptote. If we go back to the definition of an asymptote, the definition of an asymptote said as x approaches some a value, in this case -2. As x approaches -2, your y values are either going to positive or negative infinity. That's the definition of an asymptote. Here, because we can't cross the horizontal asymptote again, we know that our y values are going to go to negative infinity. Does that make sense? Okay. Now, in the middle there, where we got a and b, okay? So this is just something to pay attention to with the arithmetic. When we found a, okay, that 0, 2, of crossing the horizontal asymptote, we got that to be a solution one time, right? Okay, and a multiplicity of 1. So that means I'm going to pass through, and I'm not going to bump that asymptote come back down. Does that make sense? If you had a multiplicity of 2 or 4 or 6 or something like that when I did that word, it tells you bump it. Okay, but here we know we pass through. So if I'm going to the right from A, I know I can't go back up. I cannot go back up, because going back up, I'm going to have to cross the asymptote again, right? We know we don't do that. I know I'm going to have to go through B. Again, after B, I can't go back up. So B, and then moving to the right, is going to approach that value of 1. And I'm going to have that behavior here, that asymptote. Okay? So now, because A had a multiplicity of 1, I know that my graph is not going to do that. Okay? Some do. This one doesn't, because there's a multiplicity of 1 when I found that 0, 2 point. Okay? So then it means that if I'm going to the left of A, my graph has to get closer and closer to the asymptote, and I'm going to go to positive infinity. All right? Okay. Now, I'm going to erase this and redraw it, because it's kind of ugly looking. It's not great either. Just make that point bigger, then. But that's kind of the behavior happening between those two asymptotes. Now I have no idea what's happening on the other side of that asymptote of 1, right? Okay. So this is where I would go back to my original function, and I would use the T-chart. Okay. So I'm going to go back to this thing here, and I'm going to choose a value that was to the right of that asymptote. Well, that asymptote was 1. We're choosing an integer value to the right of that, which is 2, right? And we'll plug it in. So it's 2 times 2 is 4, minus 1 is 3, right? So it's 3 up top. Right here. Okay. Plugging 2 in, it gives me 6. That's a product of 18. On the bottom, plug 2 in again, so you get 1 and 4. Okay, 18 fourths. Okay. Which is what? 4.5? Okay. So I'm going to look at 2, 4.5. I plot that point right there. And that point right there is kind of analogous to what we did down here with C. Right? C was the only point in that region, correct? But we knew how the graph should behave to the left and to the right of C because of these asymptotes. So I should know that to the left of that point right there, I can't go down, right? Got to go up. And to the right, I can't go up. It's going to have to show that in behavior, right? I have to get closer and closer to that dotted line. Now, I don't know how fast it does that. I don't know how steep that should be. But that's going to be a rough sketch of our graph. Okay. Now, I'm going to, on top, this is what I always like to do. On top of this, I've done it by hand. We'll come back and we'll type in the actual function, 2x squared plus 7x minus 4 divided by x squared plus x minus 2. And you can kind of see that we've shown that behavior, right? Okay, now, again, the more T-chart points I plot, maybe the better I approximate the steepness of those curves in the respective regions. But our information that we found by hand is validated by that graph. Okay? All right, everybody? Okay? So that's the process every single time. Benny? Which one? The one with A and B on it? This one here? This one? Here? Okay, so we knew to the right of A we had to go through B, right? Okay. When we did the horizontal asymptote, or we crossed it, it told us that we had x equaling 0 one time, right? If it would have given me like x equals 0 twice, then that would have told me I'd bump it and go back down. Because it had an odd multiplicity, it tells me I go through it and continue passing through it. Does that kind of make sense? If we found x to be 0 3 times, it would show the same behavior. So let's do another one. Let's do let's actually I want to do this one. I want to get it on on film. We're gonna have to kind of a brisk pace here. Okay. So I'm gonna write the things we're looking for: poles, vertical asymptotes, horizontal asymptotes. And again, when I write horizontal asymptote, it means that could be slant, could be oblique. We haven't gotten to those yet. I haven't seen examples like that, and we won't until tomorrow. We want to see if we cross the horizontal. We'll find x-intercepts. We'll find y-intercepts. Then we want to do a t-chart. Those are the things we're looking for. Okay. Now, like we said, we were looking for, when we haven't seen these examples yet, but we said always look for factors that cancel. We don't have any here, right? Factors that cancel are going to yield holes. We don't have any factors that cancel, so we have no holes. Okay? Vertical asymptotes. Vertical asymptotes are where the denominator is equal to 0. Okay? So x equals 1 when that's 0, right? X equals -5 when that is 0. And x is equal to 5 when that last one's 0. Those are vertical asymptotes, right? If you've gone through the homework that I opened up yesterday, it looks long. When you look at the total number of problems, it's like 38 problems. But a lot of them are like that. Okay? Here's a rational function. Tell me where the asymptotes are. There should be a recognition of that thing, because a lot of them are already factors. Okay? Now, horizontal asymptotes. Horizontal asymptotes, we said we like to have that expanded form to look at it, right? I don't want to expand the whole thing. I don't want to do, basically, and it becomes the denominator that gives me the real issue. I don't want to take x minus 1 times x plus 5 and get that trinomial, and then multiply that by x minus 5, and then triple. That's pain in the butt. Because I'm only interested in the leading terms, right? So as long as all my x's are coming first in my factors, I'm just going to take 2 times my first term times my first term, right? And that's going to give me what? 2x squared. Okay? I'm going to do the same thing with the denominator. I got 3 times x times x times x gives me 3x cubed. Okay, so that's the comparison of my leading terms, right? Well, when I cancel those out, when I do the division there, I get 2 over 3x, right? Now, in the last example, we were left with just 2. A numerical value that told me what my asymptote was. Here, we're left with a variable expression. Now you have to plug things in. And remember, the horizontal asymptote is telling us end behavior, right? So it's telling you to plug in really, really big numbers. What do you get when you plug in a really, really, really big number there? You get 2 divided by a really, really, really big number, which would be close to 0. So my horizontal asymptote is 0. Okay? If the x was in the numerator, plugged in a really, really, really big number, you get a really, really, really big number divided by a small number, which is just still a really big number. So that tells you that your y goes off to infinity, which would indicate then you've got more work to do because you've got slant asymptote. Okay? But when we get, right now, the only ones we've worked with are when we get a numerical response or we get a variable in the denominator, and the variable in the denominator only gives you y equals 0 as your horizontal asymptote. Now I've got to see if we cross it. Okay? So if I want to see if I cross it, that means set y equals 0 and r of x equal to one another, right? So we're looking at setting r of x equal to my horizontal asymptote. Okay, so r of x is 2x plus 2, x minus 3 over 3, x minus 1, x plus 5, x minus 5 equals 0, right? That's my 0 is my horizontal asymptote. I'm asking myself, do I cross this thing? Well, how do I start solving that equation? Multiply by the LCD. Multiply by that least common denominator, right? If I do it to both sides, doesn't it just wipe away? And now you're left with that, right? Solve that. What do you get? Negative 2 and 3, right? So I cross my horizontal asymptote at x equals negative 2, x equals 3, and the both of them are having y values of 0, right? Okay. Now think about what we just did there. we just essentially, when we got this, is that our numerator equal to 0? What did that find for, in this question, what did that find for us at the same exact time? When you set your numerator equal to 0, you're finding your x-intercept. Okay? So sometimes your x-intercept, because our horizontal asymptote is our x-axis, right? So when we cross that, we're also finding x-intercepts. Okay? So that's kind of one, like Derek said in the last one, because we crossed the 0, 2 and the other asymptote in the last question, can we kind of avoid having to do the y-intercept? Absolutely. So here, because we know we're crossing a asymptote that's actually our x-axis, and we found the places that we crossed that, we don't need to find our x-intercepts. We've already done it. They're the same as those. Y-intercept, okay, I would do last times last times last, okay? Now understand that this multiple of 2 is going to impact it, right? So I do 2 times -3, gives me -6, times 2 again gives me -12 up top, right? Okay? On the bottom, I would do -1 times 5 times -5 gives me -25, times 3, which would be -75 on the bottom. Okay? So -12 over -75, right? Or I guess -12 over +75. -12 over +75. Which is 4, the 4/25. Okay. And it's -4/25, right? There's no iron. If you want to go off of the traditional way, we talked about finding a y-intercept back to algebra 1, and you said when x is 0, then by all means plug 0 in for all those x's up there, evaluate, multiply, and you're going to get -12 over 75 will reduce then to -4/25. Okay, so now we've got all that stuff. It's a matter of adding it into our graph. So we have x equals 1, x equals -5, x equals 5. Those are all our vertical asymptotes. Okay. We had a horizontal at y equals 0. Okay, so this is the reason why I like to use color and sometimes dotted lines so I can realize that I've got an asymptote over top of an axis. We cross the horizontal asymptote at x being -2, y being 0, and at 1, 0. The other one? 3, 0. Sorry. Offset 3, 0. Those are also our x-intercepts. And now we have a y-intercept of 0, -4/27. And that becomes our information. Okay? Now, when I crossed my asymptotes, were they singular multiplicities? Yeah, there were no double multiplicities when I did that. So that should tell me that however I behave around A, to the right of A, I've got to go down to get through C, right? Does it make sense that my graph's going to do something like that? To the right of A? Okay. Now to the left of A, because that was a singular multiplicity, I know I can't go down, right? I'm going to have to go up. Something like that. Okay. Now I don't know how far that black curve is getting sucked into this corner here. Okay. And I think it actually gets sucked in quite a bit. But I'm not really worried about that right now. The more points I would do, my T-chart maybe helps that. I'm not all that concerned with it. Okay. Now here in this region between +1 and +5, I don't know what's happening here at B. B is a multiplicity of 1. So my curve might do something like that, or it might do something like that. Does that make sense? So I need a value to plug in to my original function to see what's happening. So I'm either going to choose 2 or 4. I'll just use 2. I think it's going to be easier. Plug 2 in up here. I'll have 2 times 4 times -1, right? So I get -8. Down here, plug 2 in, I get 2 minus 1, which would be 1 times 7 times negative 2, right? So it's going to be oh, my fault, yeah. So it's 2 minus 5, negative. That makes more sense. So that's negative 21, negative 63. What's negative 8 divided by negative 63? Just a positive number, right? It's smaller than 1, and it's positive. That's kind of what I'm worried about here, whether it's positive or not. So at 2, I was positive. Does that make sense? So do I now know to the left of B, my graph's got to do something like that? Because B was a multiplicity of 1, my graph has to do something like that. Okay? Now I've got on the outskirts of my graph, so left of negative 5 and to the right of positive 5. I have to do the same thing. Okay? I have to go back in and choose a value like negative 6. And that's kind of a pain in the butt. So try negative 6 and plug negative 6 into here. 2, negative 6 would give me negative 4, negative 9, so that's 72. And then down here it'd be 3, negative 7, negative 1, negative 11. So that negative 7 is negative 2, is that negative 231? Huh? Right, so this is negative 231, right? Am I right? Okay. So that quotient is negative, so negative 1/3, right? Okay, so graph that. So here, negative 1/3 would be right there. So then we're below that asymptote. We get substitute that way. We substitute that vertical in that way. Okay. Now do the same. You would do the same thing for 6. I'm not going to do 6, but I do know that should look like that. Or 6. And if you were to go on top of that and graph it with GeoGebra visibilities, you're going to find that out. Okay? So look the exact same thing. Is that all right? Okay. I want to do one more real quick, and it explains what happens around a hole. All right, so holes are found when we have common factors in the numerator and the denominator. Okay? It's the first thing that you're going to do. You're going to recognize whether you have cancellation occurring. Holes kind of dictate or override, I guess, asymptotes. So if I were to factor this S of x, okay, it's going to look like x minus 3 over x times x minus 3, right? That is a set of factors that cancel, correct? So when they cancel, what am I left with in the top? All right. All right, so those two functions that I put boxes around are they're equivalent graphs. They look exactly the same, except this one's going to have a hole in it. The hole is found at the 0 of that common factor. So set that common factor equal to 0, and you would get what? 3. Okay? We have a hole at x equals 3. Now, there's an infinite number of y values when I have an x value of 3. I got to find out which one of those y values it is. So how do I find a y value? I take this and plug it back in. Let's think about this. Can I plug it back in here? No. So what do we have to plug it back into? The depreciated one, the canceled one. Okay? So what do I get when I plug x back in here? 1/3. So you have a hole at 3, 1/3. Okay? Once you do that, once you find all your holes and you cancel, and you have this I call it the depreciated function, 1 over x. You now find your horizontal asymptote, your vertical asymptotes, your x-intercept, your y-intercept with that depreciated function. Is that all right? When I look at that 1 over x, what's the vertical asymptote? What can I now divide by here? 0. So x equals 0. Horizontal asymptote. When I compare those leading terms, 0, right? Okay. So when I graph this thing, Okay, look at, let's just go 1 over x. That's that graph 1 over x, right? Okay, but if I evaluate that at 3, it gives me something back. It gives me 1/3 back, right? Does that make sense? Okay, that's not what we want, because what we really want is x minus 3 over x squared minus 3x. Does that look like 1 over x? Does that look like the same exact graph? Yeah, it looks the same, right? Okay, but the difference is when I evaluate this one at 3, it spits back a whole, right? So we need, the way I always do it, I need to go 3 1/3, and I need to put an open hole there, an open dot, and that reminds me that that is what we call point discontinuity, okay? But if you look at that, your asymptotes are still the same as what they were for 1 over x, right? Okay? Because you have a asymptote that is y equals 0, and we can go 1 over x equals 0. 1 over x equals 0 and solve that equation. We don't cross it, so we don't cross the horizontal asymptote here. So if I don't cross the horizontal asymptote, I don't have any x-intercepts. Does that make sense? Okay? I have a vertical asymptote at x equals 0, so I don't have any y-intercepts either. So technically, if I was going to try to find that portion of the curve right there, I would probably want to go to a t-chart, or maybe I've stored in my mind what the parent function 1 over x looks like, and I can do it that way, or go to a t-chart and evaluate. Okay, but that's how you approach holes. Is that okay with everyone? You might have 2, you might have 3, you might have 1. Sometimes you don't have any. Okay, it's just something you got to pay attention to. I sent out yesterday a schedule for the rest of the semester. I'm going to try to do my best to abide by that. I also sent out a practice test. The test on Thursday will be very similar. We'll talk about it more tomorrow. We'll send out a key here in a little bit for that. Have a great rest of the day. Except for you. Good.